Hello, welcome back. Today in this lecture, we will learn about the mechanical properties of ceramics, mainly the experimental methodology to determine the mechanical properties of ceramics. For the tribological applications, mechanical properties such as hardness, elastic modulus, strength and fracture toughness are very important properties. So, the influence of these properties will be reflected on the tribological performance of these materials. So, it is very much important to learn about the methodology to determine the properties of these ceramics. So, mechanical properties of metals and polymers are measured in a different way than what we measure for the ceramic materials. So, first hardness. Hardness as per the definition is the resistance against the permanent deformation. If one material is trying to deform the other material is relatively softer than the material, then you have a response is nothing but a deformation. So, if any harder material is trying to penetrate into the softer material, then after this penetration there is a response. If the response is a permanent deformation, then we say the material, this material is less in the hardness, right, or the material is softer. So, the resistance against the permanent deformation is hardness. So, this hardness of ceramic materials are generally measured by Vickers indentation. In the Vickers indentation, a indenter which is of diamond is used. This diamond indenter having a square based pyramidal indenter, it is a diamond square based pyramidal indenter. So, the opposite faces of which has around 136 degrees angle. So, such an indenter is pressed on the surface of your sample. So, once you release the loading, then you get an impression. The impression is a perfect square impression. So, the square impression is measured for its diagonals, right. So, the diagonals are measured, average of the diagonals is measured, then you will know the hardness of this material is equal to 1.854 into the load applied divided by d square. D is the average diagonal length of the square impression. So, this number actually came from this sine of 136 by 2 into 2, right. So, this will give rise to this 1.8544, right. So, hardness is expressed in pascals if the load applied is taken in Newton, right. So, or you can say if load applied is in kilograms, then you multiply the hardness into hardness number into 0.009807, then you get a hardness in gigapascal, right. So, generally ceramic materials have higher hardness more than 10 gigapascal, right. So, certain ceramic materials like boron carbide, silicon carbide, titanium diboride, these materials have extremely high hardness of around 25 to 30 gigapascal. So, the Vickers indentation is to be done very carefully to obtain the hardness of the ceramic material. So, the indent load should be taken in such a way that it does not crack from the indent corner, it does not give any cracking from the corners of this indent, right. We will select a load where there are no cracks generated from the corners of this indent, such a load is taken. In addition to that, the indentation developed shall be without any spalling or damage around the indentation. Generally, we will have some damage around the indentation. So, we will select the load such that the damage is not there around the indentation, right. And it is also suggested that the hardness of a new ceramic composition processed using a new synthesis or the sintering routes that we will see later. So, such a hardness be measured using various indent loads. right. So, if you see here the hardness is proportional to the load here, right. So, and then inversely proportional to the square of the impression. So, if there is a load applied and then hardness is measured with respect to the load, as the load is increased you will have bigger impression, right. Smaller loads a smaller impression, larger loads a bigger impression. So, you will have certain indentation effect, that means the hardness decreases with the load. So, this could reveal the indentation size effect and a conservative estimate of the true hardness could be obtained. So, it is suggested that hardness of a new ceramic composition processed using a new synthesis route be measured using various indent loads. It is also recommended to measure the indentation length, right, the diagonals of the square impression using scanning electron microscope rather than using the optical microscope. So, that the length are measured very carefully. So, generally the impression is in micron meter order. So, if there is a error in measuring this micron meter order length, there will be a large difference in the hardness we are obtaining. So, there will be error in hardness measurement which is generally expressed in gigapascal. So, this would provide a reliable value for hardness of a ceramic material. So, better we use more sophisticated techniques to precisely measure the diagonal lengths. For example, the scanning electron microscope to be used to measure the indent diagonals precisely. So, Vickers indentation shall be done at a load where it does not cause cracking from the indent corners and it shall not have any result of this spalling around the indentation, or you must take at various indent loads so that it could reveal the indentation size effect. It is better if you use the scanning electron microscope than the optical microscope to measure precisely the diagonal length, which is generally in the order of micron meter, right. So, the other method where the ceramics are measured for their hardness property is a Knoop indentation. So, Knoop indentation is also similar to Vickers indentation, only difference is the indenter in the form of elongated diagonal pyramid. So, in the Vickers indentation is the square based pyramidal indenter, whereas here you have along one line, along one direction there is a longer diagonal than the other direction, that means indenter in the form of elongated diamond pyramid. So, the hardness is measured again load applied divided by the area. So, you take the ratio of the load applied to the indenter to the uncovered projected area, generally taken P divided by C L square. A is the length of the longer diagonal of the impression and C is a constant that relates the projected area of the indentation to the square of the length of the long diagonal. So, generally it comes about 0.07. So, you get a hardness again in gigapascal. So, but this Knoop indentation produces a diamond shaped indentation having an approximate ratio between the long and short diagonals as 7:1. The depth of the indentation is about 1/30th of its length. Knoop indentation is also used for determining the hardness of ceramic material, right. So, let us go to the other mechanical property, that is strength. Strength is nothing but the load bearing capability of a material, right. So, but ceramics, if you measure the strength in a tensile loading condition, it is very difficult to have a reliable data, right, because first of all it is very difficult to have a dog bone shape specimen, because the machining of a ceramic material is itself a difficult task, right. The moment you start machining to that shape, that will fail, that will fracture. If you have somehow some non conventional machining type of things are used to somehow make such a dog bone structure for the tensile testing. So, but you have to grip it at the edges, right. So, while gripping itself the material may crack, but even though if you could able to manage to measure the tensile strength, so the fracture will occur at a very less strains of 0.01%. So, it is not reliable to have certain strength in a tensile loading condition. The strength is always measured in a compressive loading condition for ceramics. So, although ceramics are extremely weak in tension, as I told, very smaller strains, at very less strains the failure will be occurring. So, although ceramics are extremely weak in tension, they have superior compression property. So, the difference can be attributed to the difference in microstructural resistance to the growth of the crack and nature of the crack propagation under two different loading conditions of tensile and compression. So, you get a difference in the response of this material. So, the load bearing capacity in compression loading condition is much more than the tensile loading conditions for ceramic material, right. So, we better go determine the strength in a compressive loading condition. So, for the compressive strength determination, generally a cylindrical sample with aspect ratio of 1 or above are typically used. So, the compressive strength can be calculated from the fracture load and the dimension of the sample using the simple formula that compression strength is equal to P by A, where P is the load at which the fracture is occurring, A is the area of the sample. So, ceramics behave like perfectly linear elastic material up to fracture, right. If you see the stress and strain even in the compressive loading condition, so you have almost linear relation between stress and strain up to this elastic limit, and after this the material yields and then immediately after yielding starts there is a fracture. So, there is a very small amount of plastic deformation before fracture. So, ceramics behave like a perfectly linear elastic material up to fracture and in a non-linear manner after reaching a load much higher than what it was in the tension, right. So, in tensile in contrast to tensile crack growth, the cracks generally extend vertically along this compression loading direction. So, if you have a material and compression loading condition is applied, all these cracks inside this material will be aligned themselves to along this direction of this compression. So, you see, so they align and they coalesce each other and then form a bigger crack front that leads to the fracture. So, because of these the serrations are observed. So, serrations are essentially due to spalling of the small test volume as the growing cracks either coalesce with each other or meet the unconstrained surface of the material. So, you get generally these striations. So, because of this delayed fracture, the compression strength is much more than the tensile strength. It is generally found 8 to 10 times more strength in compressive loading conditions than in tensile loading conditions for the ceramic material. So, we will also see that in the other class that there are certain secondary cracks growing because of this reorientation with respect to the compressive loading conditions, right. So, the secondary cracks will also consume certain amount of energy. So, the major crack will not be propagated easily. So, that means there is a difficulty in the crack propagation, that means the fracture is delayed. So, the delayed fracture behavior is realized in compression. So, the resultant of which we see the compression strength is around 8 times higher than the tensile strength, right. I must tell you, for ceramic materials, for example, aluminum oxide, the compressive strength is around 1000 MPa, is 800 to 1000 MPa. In tensile loading conditions, the strength is around 300 MPa, right. Whereas, in steel materials, plain carbon steel materials, either in compressive loading conditions or tensile loading condition, the strength is around 250 MPa. So, there is a large difference in strength in compressive loading conditions to tensile loading conditions for ceramic material. So, 300 to 350 MPa for in a tensile loading condition, that strength, and it 800 to 1000 MPa in compressive loading conditions are typically observed for aluminum oxide ceramic materials. So, the other way to measure the strength is by bending, right. So, again considering the fact that tensile sample preparation for ceramics is a challenging task, the strength of the ceramics is measured in a compressive loading condition or in other way by flexural mode, right. What we do, we take a specimen and try to bend it by application of a load. So, we may have a 3-point bending or 4-point bending method for determining the flexural strength. The flexural strength is calculated on the basis of the load at which the fracture occurs and the dimension of the test sample. So, during this flexural testing, the loading surface is in compression. So, this is in compression and the opposite surface is in under tension. So, the stress value linearly decreases along the thickness direction of the sample till the neutral axis. So, as I told, it can be measured, the flexural strength can be measured by 3-point bending or 4-point bending configuration. So, what is 3-point bending? The load is given at the one surface, top surface of this material. For example, a rectangular block, right, having certain dimensions B and D. So, this load which is applied on the top surface is supported at from two different locations from the bottom surface. So, as I told, the top surface is under compression, right, the loading surface is under the compression. So, you increase the load, right, at certain load the fracture will happen. So, you note down the load at which the fracture happens, that is the P, and L is the span length and B is the width of this sample and D is the thickness of the sample, right. So, for a rectangular specimen, the flexural strength in 3-point bending configuration becomes 3 P L by 2 B D square, right. In a 4-point bending configuration, the load is more distributed. The 3-point bending concentration, the load is concentrated. In a distributed loading conditions like a 4-point bending configuration, the load is applied at two different locations on the top surface. Half of the load is applied at each location on the top surface and it is again supported from two locations from the bottom surface. The flexural strength is equal to 3 P L by 4 B D square. Actually, this L is equal to L minus Li, Li is the internal span length from here to here. So, generally it is L by 2, so it becomes L by 2. So, L 3 P L, the L becomes L by 2, so it becomes 3 P L 4 B D square, right. So, for a rectangular block specimen, the 4-point bending strength is equal to 3 P L by 4 B D square, where P is the load at which the fracture happens, that we call fracture load, right. So, comparing these two, in case of 4-point bending, maximum tensile stress is distributed over a larger area, right, larger area of the sample as opposed to the 3-point bending flexural mode. So, we will get a lower and more conservative estimate of the strength in 4-point bending test, right, and the strength can be measured in a diametral compression approach as well. So, actually in a diametral compression approach we can determine the tensile strength. Again, since the preparation of a standard tensile sample from brittle ceramics is extremely difficult, an alternative approach which is diametral compression can be adopted to measure the tensile strength of the ceramics. You see, we do diametral compression, but we get the result as a tensile strength. So, a cylindrical sample is taken, right, a cylindrical sample is taken which has much larger diameter than the thickness. So, such a cylindrical sample is loaded in pure compression loading conditions, right. So, you increase the load. So, at peak load the entire disc fractures into multiple fragments with failure predominantly along the compression axis. The tensile strength measured in a diametrical approach sigma equal to 2 P by pi dt, right. T is the thickness of the sample, d is the diameter of the cylindrical sample. So, generally while measuring such a tensile strength from the diametral compression approach, to reduce the shear failure which can occur from point loading in diametral compression test, Generally we use certain copper strips, or we generally go for distributing the load over a controlled volume, right. So, to reduce the shear failure resulting from point loading in diametral compression test, we usually go using the packing strips, generally copper, or we usually go for distributing the load over a controlled volume. So, strength can be measured in a diametral compression way also. This strength is a tensile strength actually, right. The other mechanical property is the elastic modulus. Again, elastic modulus can be measured if you have a tensile stress sample or in a compression loading condition or a tensile loading condition. So, you see the sigma versus the epsilon, the stress versus strain response. So, the slope in this linear region of this stress strain response for a material can be taken as a elastic modulus, right. The slope is nothing but an elastic modulus. But brittle materials, after this elastic deformation, the fracture occurs. So, but it is a destructive test, right, but we can actually measure the elastic modulus by non-destructive test as well. So, generally this is done by impulse excitation technique. So, you take the steel ball and you use this steel ball impulse to excite the sample, right. The response is the vibration. The frequency of vibration is strongly dependent on the shape, dimension, mass and stiffness of the sample. The vibration response is recorded using accelerometer or microphone. Accelerometer for the contact sensors, or you can use the microphone, that is a non-contact sensor. So, the frequency of such vibration is strongly dependent on shape of the sample, dimension of the sample, or the mass of the sample and stiffness of the sample, right. So, you can see certain sensing points like a non-contact sensor, whereas impact is done with a contact sensor. So, there are certain formulae to determine the elastic modulus. So, either of these formulae can be used to determine the elastic modulus. So, where m is the mass and ff is the flexural frequency, b is the width of the sample, L is the length of the sample, T is the thickness of the sample, D is diameter if the sample is of cylindrical. So, F cylindrical, right. So, Fi is the natural frequency, natural resonance frequency, generally 1 2 corresponds to first and second mode, etc. So, nu is the Poisson's ratio, K1 is the geometric factor and obtained from the empirical relations, and T1 T2 are correction factors, again they are factors based on the dimensions of this sample. So, we do not need to go details about this formulae, but it is better to note down that there are certain non-destructive tests, non-destructive way to determine the elastic modulus of such material. Particularly this is very much significant because ceramics are brittle. To prepare a specimen for the tensile testing, it is very difficult task. So, these kind of techniques are generally used, and impulse excitation technique is generally used for metals, glasses as well, in addition to the ceramic materials. There is one more method where the elastic modulus is generally reported for ceramic materials, is by ultrasonic method, right. So, what we do, we take a specimen and then send ultrasonic waves from one side of the specimen to the other side of the specimen. You know the specimen thickness, right. So, thickness. So, you note down the time required for this wave to go and touch the other end of the specimen and come back, right. So, you by using an oscilloscope you can determine what is the time. So, you know the thickness and what is the thickness, you know the time. So, you get the velocity, right. So, the distance upon the time, velocity. So, you measure certain velocity of these waves in a longitudinal or shear waves, right. The thickness of the samples and the travel time of the waves across the thickness of the samples can be used to estimate velocities of the longitudinal or shear waves. You get these longitudinal and shear waves, and then you get a elastic modulus if you know the Poisson's ratio. So, longitudinal velocity and shear velocity of these ultrasonic waves are estimated, and these are used to determine the Poisson's ratio. This Poisson's ratio is used to determine the elastic modulus, right, elastic modulus. So, where rho is the density of the sample and CL is the velocity of the longitudinal wave and the CS is the velocity of the shear wave, both are in meters per second. So, but you must note down that the elastic modulus data obtained by ultrasonic method is not much reliable, because the material is not perfect, right. The material has lot of defects, for example cracks, pores or any other defects, right. So, the ultrasonic waves may also come back after hitting these cracks, right. If there is a crack in between, so the ultrasonic waves may come back. So, you get a error in the time estimated for the longitudinal or shear waves. So, you get an error in the Poisson's ratio or elastic modulus data, it is not much reliable data. So, the other way to measure the elastic modulus is by instrumented indentation. So, instrumented indentation is also used for hardness measurement. In this instrumented indentation for the elastic modulus and hardness generally done by Vickers indentation or Berkovich indentation. Vickers indentation, we have seen that Vickers indentation is a diamond pyramid indenter is used, which is a square based indenter, square based pyramidal indenter, whereas Berkovich we have a 3-sided pyramidal geometry. So, both are made by diamond only, right. Those small loads are applied and the tip sizes are also small. The displacement and load are recorded simultaneously during loading and then unloading. So, you can see the loading, it goes to the maximum and then comes back unloading. So, the elastic modulus can be determined by this recording of this load and the displacement, right. The Young's modulus can be determined by the reduced elastic modulus. The Young's modulus can be determined, the E can be determined by this reduced modulus ER, and EI is the modulus of the indenter. So, we know it is a diamond. So, we know the value. So, the nu is the Poisson's ratio of this material and nu I is the Poisson's ratio of the diamond indenter, Berkovich indenter. So, we know this ER is again calculated by S and A, right. S is the stiffness parameter and stiffness is usually obtained while unloading the slope. The slope while unloading, the slope of this load and displacement curve while unloading is taken as the S. So, A is the area of the impression, right. So, the area can be determined as a function of this displacement. So, A is determined by certain functions. For a perfect Berkovich indenter, it is to A equal to 24.56 into Hc square, Hc is the displacement one, and you know the maximum load applied divided by this area, you get hardness also. By instrumented indentation, elastic modulus and hardness both can be measured, but we must note down the while initial slope of the unloading response, right, in case of the instrumented hardness measurements provide an estimate of the elastic modulus. The slope of initial linear loading response under uniaxial compression, flexural or diametral compression can be used to determine the elastic modulus under respective loading conditions, whereas the first one both are used for measuring the elastic modulus, right. So, after this elastic modulus, let us go to the other property, which is fracture toughness. Fracture toughness by definition, it is the resistance to propagation of an existing crack. So, you have a ceramic material, right. So, there are certain cracks oriented in different directions and having different sizes, right. So, the resistance to propagation of this crack is nothing but the fracture toughness. So, for metallic materials you have a toughness parameter which is more relevant, right. The toughness is nothing but, if you know the stress and strain, the area under the curve is the toughness, or you must say You can also say the energy required to break a unit volume of a material is toughness, right. So, but in ceramic materials, because of the sensitivity towards the cracks, so because of the strong influence of the crack propagation in fracturing the material, so the resistance against the propagation of existing crack is taken as a parameter to understand such toughness. So it is named as fracture toughness. The fracture toughness is the resistance to propagation of an existing crack. So existing crack means there is certain physical dimension of the crack. So the fracture toughness can be measured by different techniques. The fracture toughness, if they are measured by different techniques, generally we get a different value of fracture toughness. So there are two methods for measuring the fracture toughness of a brittle material, a long crack method and a short crack method. In a long crack method, generally single edge notch beam technique or a modified single edge notch beam technique called single edge V notched beam technique are used, whereas short crack method, it is indentation, Vickers indentation is used to generate cracks, and then these short cracks right, after this indentation the cracks generated at the corners of this Vickers indentation impression, right, these cracks are measured and the crack length is taken for determining the fracture toughness by indentation method. So let us see these, the single edge notch beam technique. So compressive loads are applied in cycles in a to a specimen with a cut notch. So you take a specimen, right. So there are certain ASTM standards for preparing this specimen for the single edge notch beam technique to determine the fracture toughness of a ceramic material. So what do? You cut a notch, right, a notch having certain length, certain dimension C. So you know what is the initial dimension of this crack. So the compressive loads are applied in cycles to a specimen having such a notch of certain dimension. So this results in damage accumulation, so that leads to crack growth in the zone ahead of the notch when loaded in this flexural mode. So as I told you, the flexural mode can be 3-point bending configuration or the 4-point bending configuration. So this illustration is given for the 4-point bending configuration. So either way you can apply this load and then see at what load the fracture happens, right. This is the fracture load, that means the load at which the fracture occurs. L is the length of the span, H and D are the dimensions of the specimen, C is the notch length. So and Y is the parameter again dependent on the length of the crack and the height of the specimen, right. So we can determine what is the K1C value. The K1C value is actually, C indicates the critical, K indicates the stress intensity factor. So 1 indicates the mode 1. There are actually 3 modes for crack opening. So mode 1 is the tension and mode 2 is sliding and mode 3 is tearing. So crack can be opened up in a tensile mode. When it is opened up in a tensile mode, easy to coalesce such a crack, and then that leads to longer size of the crack. So when the size reaches the critical value, there is a spontaneous propagation of a crack and that will lead to fracture. So sliding mode is another mode of crack opening, where the crack is generally opened in a sliding mode, whereas the tearing mode is another mode of opening a crack. Out of these, this opening in a tensile mode is much dangerous. So most of the studies are done to determine the fracture toughness this stress intensity factor of a brittle material in a mode 1 crack opening, though the stress intensity factor is a fracture toughness parameter. So the fracture toughness parameter, the stress intensity factor K. So K1C means critical stress intensity factor in mode 1 crack opening. So K1C equal to Y into 3PL by H square D and into C power 1 by 2. So Y is again determined with the help of the specimen thickness and the crack length. So you can have the K1C value for a brittle material, and this is the most precise measurement for the K1C, that is fracture toughness measurement, fracture toughness. There is a slight modification for the SENB technique. So, here the notch is given as a V shape, right, V shape. So, it is actually zoomed here. You see there is a V notch. So, a sharp V notch is produced by polishing the notch root with a razor blade coated with diamond paste. It is actually a difficult task, right. So, again after this notch you apply the loading conditions, so that there is a flexural loading and then fracture occurs. Again you determine the K1C. So, where P of A is the load at which the fracture happens, and L0 is the outer span and Li is the inner span in this 4-point bending mode, right, and B is the specimen width and W is the specimen depth. So, alpha, this is alpha is actually the pre-crack size divided by this W, right. The pre-crack size is actually taken as A. So, again there is a function of this alpha which again can be determined with respect to the geometry of this testing condition. So, we do not need to go into details of this one, but we must note down there is one more method which can precisely give the fracture toughness value. This is single edge in V notched beam technique, which is slight modification for the single edge notched beam technique. The last one is the indentation fracture toughness method. The toughness, the fracture toughness measured by indentation method. So, generally as we understand, after this Vickers indentation there is a square impression, and from the corners of the square impression there is certain crack, right. So, in 4 corners we have certain cracks developed. So, these cracks are median cracks which extend from the corners of this Vickers indentation. These median cracks which extend from the corners of a Vickers indentation are arrested when the residual stress driving force, that we call K residual, at the crack tip is in equilibrium with the fracture toughness. So, if you can say the residual stress factor here, and then P is the load at which the indentation is done, C is the crack length. So, from here to here this is the 2C, right, this is 2C, this is also 2C, right, this is also 2C. So, 2C 1, 2C 2, so you get a average of 2C. So, from here you get a C value. The P is the load at which the indentation is done, H is the hardness from the Vickers indentation. Again we know H is equal to thus 1.8544 into load applied divided by the square of the average diagonal length, right, this average diagonal length. So, you get the H value. E is the elastic modulus of the specimen. So, elastic modulus, hardness, the load applied for the Vickers indentation and the crack length. So, this is the fracture toughness value, it is in equilibrium with the residual driving force at the crack tip. So, you know the residual stress factor, and then again, so this is a fundamental relation for the fracture toughness in equilibrium with the residual stress driving at the crack tip. Based on this concept, there are several formulae developed for the ceramic material. Based on this formula, based on this concept, there are several formulae developed for different ceramic materials. The very important of which is the Anstis one. Anstis formula says that the A, here you can see the A is 0.016 and N here is 1/2 and here C by C. So, the K1C equal to 0.016 into under root of A E by H into P divided by C power 1.5. So, that means for smaller crack length K will be higher, right. So, and recently there is the other group of researchers provided a modification for this Anstis formula, just a change in the constant 0.019 instead of 0.016. These are semi empirical formulae developed based on the data obtained for ceramic materials. So, now we know the indentation gives the cracks at the corners of this Vickers impression, right, but These cracks can be mainly of two types, a Palmquist crack or a median crack. Generally these are the median cracks, right. So, if you see the before polishing, that means after indentation is done without doing polishing, you can see the impression and then the cracks generated at the diagonals. In both cases it is same, but if you polish it and remove all the strains there, and then after polishing you see a different characteristics, and this is Palmquist crack, right, Palmquist crack, this is a median crack, radial median crack. So, and radial median crack and the Palmquist cracks are related with L is equal to C minus A, right. L is the Palmquist crack length, C is the half of the total crack generated from one side to another side, or C is the length of the crack measured from center of the impression to the edge of the crack, right. So, L and C are related, that L is the Palmquist crack and C is the median crack, and both are related with the relation L equal to C minus A, right. So, Palmquist cracks are generally generated in a low load conditions, right, and when the L by A, this one, the L by A 0.25 is less than L by A less than 2.5, then Nihara proposed a formula, right, whereas the C by A, if it is more than 2.5, the formula is different. As I told, these are based mainly on the experimental data obtained from the different ceramic classes. So, recently the Shetty et al. also modified the Nihara formula, where K1 is equal to 0.025 E by H whole power 0.4 into H W whole power on 0.5, where W is equal to P by 4A, where P is the indentation load, 2A is the Vickers diagonal, average of the Vickers diagonal. So, we will see in several case studies these formulae are used to determine the fracture toughness easily by this indentation method, right. So, this Shetty formula is generally applied for the Cermet materials, right, Cermet materials, where these are generally used for different ceramics and ceramic composite materials. So, we must note down this indentation fracture toughness or the fracture toughness measured by the indentation method are less reliable, right. They are less reliable. First of all, they are less reliable. The fracture toughness data is less reliable, but it is generally used frequently. The fracture toughness is determined generally by the indentation method, because there is hardly any preparation required for the testing, right. So, whereas in other methods you have to prepare a sample of this geometry, right. So, preparing such a sample of this geometry is itself a difficult task for a brittle material, right, and in addition to that you have to give a notch of a particular dimension. So, giving this notch is itself a difficult, right. So, it is very difficult task, but once you get this, the data obtained by this technique is much reliable. That means, the fracture toughness obtained by this long crack method is much reliable and precise, right. It can be reproducible as well, whereas the fracture toughness determined by indentation method is less reliable and it is not precise, and it cannot, the reproducibility is also very less. So, but it is still used, as I told, because of the simplicity in the procedure. There is no preparation of the material, only the surface has to be flat, right, and then the indentation is done. After the indentation, impression is measured for its diagonal, and the crack lengths from the length of the cracks from the corners of this indentation impression are measured to determine the fracture toughness. So, this type of indentation fracture toughness is generally used when you want to rank a material, right. So, you have several ceramic composites. So, generally for the study purpose we take a material A, material B, material C, material D, and these are differing only in the composition, right, or certain material parameter is only differing. So, we know only difference is because of certain material parameter. So, the response is the result we get in the difference in the K1C value. So, K1C value of A, K1C value of B, C, D. So, we do not say this K1C value of this certain class of material is exactly the what you are getting, but you can actually rank them. So, that means the fracture toughness value of B is higher than the fracture toughness of C or lesser than the fracture toughness of D. This kind of analysis or this kind of understanding is obtained by this fracture toughness by indentation method. We do not use the data obtained by indentation method for precisely mentioning the fracture toughness of that material, but we use this data to relatively rank the material. So, only for that purpose this indentation fracture toughness is still valid. So, people are still doing, otherwise for the precision point of view the other method, which is a long crack method, is much more reliable, right. So, the fracture toughness values for the ceramic materials are generally less than 10 MPa root meter, right, 10 MPa root meter. So, if you see these units, it comes as MPa root meter, right. Just for comparison, other materials like metals, right, they have very higher fracture toughness. For example, plain carbon steel have a fracture toughness of around 80 to 100 MPa root meter. That means the metals have higher fracture toughness, at least one order of magnitude higher fracture toughness. Ceramics are inferior with the fracture toughness point of view, that means they are inherently brittle, the propagation is much spontaneous. So, that means the resistance to such propagation of a crack is very less for the ceramic material. That means the fracture toughness value K1C value is very less compared to the metallic materials fracture toughness, right, or the polymeric materials fracture toughness. So, summarizing today's class, experimental methodology to conduct mechanical property evaluation of ceramics is mainly discussed in this lecture, and mainly we focused on very important properties, mechanical properties, hardness, strength, elastic modulus and fracture toughness, the influence of which will be observed in different case studies done for different materials of ceramics or ceramic composite materials. The hardness by definition is the resistance against permanent deformation, strength is the load bearing capability, elastic modulus is the ratio of stress to strain in the elastic regime of stress strain curve, whereas fracture toughness is resistance against crack growth, right. So, thank you.